Hello, this is Truth Socrates. Welcome to a portrait of linear algebra. Now, if the words in our title for the video today look familiar to you, of course, it's because we saw them back in chapter 3. So today we are going to generalize the concepts of injective transformations, surjective transformations, and we will learn how to find the compositions of compatible transformations. So, we're obviously going to generalize the definitions for injective and surjective transformations. Now, back in chapter 3, we had the kernel test and the rank test for transformations on Euclidean spaces. So we will see, of course, that those tests generalize for transformations on abstract vector spaces. We will see how to use the matrices for a linear transformation that we constructed in our last video to find a basis for the kernel and the range of the transformation. And of course, this will allow us to decide whether a transformation is injective or surjective, both or neither. We are also going to learn how to compose two transformations if they are compatible with each other. How can we find the matrix of a composition in terms of the matrices of the two individual transformations? And in particular, we are going to learn how to compose an operator with itself. If the domain and the codomain are exactly the same, then we can apply the operator one more time to itself. Okay, so let's get the definitions and the theorems out of the way. And we're going to look at a very comprehensive example at the end. So, definition for an injective or one-to-one function is exactly the same as in chapter 3. We say that the transformation is injective or one-to-one if the image of different vectors from the domain are different vectors from the codomain. In other words, if V1 is different from V2, then T of V1 is also different from T of V2. So that's also called an injection or an embedding. So we can turn these inequalities into equations as usual by finding the contrapositive of this sentence. So theorem, although it's really just a step up from the definition because it's just a contrapositive. A transformation is injective if and only if the only way two vectors from the domain have the same image in the codomain is for them to be the same vector to begin with. If T of V1 were the same as T of V2, then V1 had to be the same as V2. So the only solution to the equation T of V1 equals T of V2 is for V1 to be equal to V2. There is no other solution. The proof for the kernel test in this chapter is exactly the same as the proof in chapter 3, with just the notation changed a little bit. So a transformation T from V to W is one-to-one if and only if the kernel of the transformation is only the zero vector in the domain V. Okay, so let's take a look at surjective transformations. And here is a diagram that summarizes both of those definitions. So a transformation is surjective or onto if the range of the transformation is all of the codomain. The range of T is W. Now, if W is known to be finite dimensional, then again we have the rank test. Since the rank of P is the dimension of the range of T, we can also say that T is onto if and only if the rank of P is the dimension of W, when W is known to be finite dimensional. Alright, so this diagram summarizes those two definitions and the theorem. So T is injective. You don't see two arrows going to the same vector in W if and only if the kernel of this transformation is only the zero vector. So in particular, the only vector in the domain that goes to the zero vector in the codomain is the zero vector in the domain. There are no other vectors that transform to the zero vector in the codomain. So similarly, your transformation is surjective if and only if the range of the transformation is all of W. So in other words, if you take any vector W in the codomain, there is a vector in the domain that transforms into that vector. All right, so back in chapter 3, when we first saw those two words, kernel and range, we immediately said that the kernel is just the null space and the range is just the column space. Okay, but now we have linear transformations of abstract vector spaces. So in particular, we don't have a single matrix for these transformations. What you have to do is pick a basis for the domain, pick a basis for the codomain, and then make the matrix of that transformation. Okay, so here's the setup, just like as we did in our last video, to make the matrix of that transformation. Then we can go ahead and find the REF of that matrix. So we're back in chapter 3. Okay, the REF will tell you about the null space of that matrix. But this time, the null space of that matrix is not enough. Okay, we need a set of vectors from the domain. Okay, so all you have to do is basically decode your null space basis, right? Take the first vector in your basis, right? There is one vector, exactly one vector in your domain, whose coordinates are given by z1. Okay, that's the decoding process that we saw in the last video. Okay, do that for every vector in your null space basis. Find a corresponding vector in V whose coordinates are those vectors. What you get is a basis for the kernel. Okay, and of course, if there are no free variables, then the null space is just the zero vector, and the kernel is just the corresponding zero vector. Okay, now we also have the minimizing theorem in chapter 3. So look for the columns in the REF that contain a leading 1. Okay, and then go back to the original columns of your matrix for T. What you see are coordinates for a corresponding basis consisting of vectors from the codomain. Okay, so this time we decode the columns of the original matrix using the basis B prime for the codomain. Okay, look for the unique vector in the codomain whose coordinates are the first column, the second column, and so on in your column space. Okay, and those vectors put together will form a basis for your range. So in other words, okay, forget this whole theorem. All right, too long, too confusing. Just think of the matrix of the transformation with respect to the two bases. Look for the REF. As usual, find a basis for the null space, find a basis for the column space. But don't stop there. Okay? Use the basis for the null space to find actual vectors from the domain, and those will be your basis vectors for the kernel. Okay? Similarly, look for vectors from the codomain whose coordinates are the columns that you pick, and those vectors will be your basis for the range. So it's all really a matter of decoding with respect to your basis B for the kernel, or with respect to your basis B prime for the range. Okay, so as promised, here's an example that will demonstrate everything that we saw in the last few minutes. Okay, so here's a transformation from P4 to P3. It looks ugly and complicated, but don't worry, we'll break it down. And here's a basis for the domain P4, 1x, x squared, 2x to the fourth. So again, it's a 5-dimensional vector space. And for P3, our codomain, we will use 1x, x squared, x. It's a 4-dimensional vector space. Okay, so here's our to-do list. We are going to verify that this is actually an additive transformation. So we will leave homogeneity to you. Okay, we will construct the matrix for this transformation using these bases. So that's a good review from our last video. We'll find the REF, one click, and from the REF, we will construct the basis for the null space and then the kernel. And similarly, we will construct the basis for the column space and then the range. Okay. Last thing we'll do, we'll decide if our transformation is injective or surjective or neither or both. Okay, actually, you know what? Let's think about that for a minute. Okay, you probably already know the answer. We're going from P4 to P3. Okay, bigger dimension to a smaller dimension. So we saw this in chapter 3. If you're going from R5 to R4, that's the perfect analogy here because that's 5-dimensional, that's 4-dimensional. Okay, which of the two properties is impossible for P? Bigger to smaller. Okay, so it's like you're cramming your foot into a shoe that is too small and too tight. Okay, it's gonna hurt. So you're going to fail injectivity. You cannot possibly be 1-to-1. So that means that we will have a non-zero kernel as our answer. Okay, definitely not 1-to-1, but it could be onto. It doesn't have to be onto, but it could be onto. All right, so our first task is to verify additivity. What would happen if we got T of P plus Q? Will we get the same thing as T of P plus T of Q? Okay, so let's copy this down over here, and we're going to change it. All right, so we want the left side to be T of P of X plus Q of X. Right? So what that means is that we have to replace P, which appears 3 times, with P plus Q. So I will copy this, and I will erase P and put in parentheses. There you go. Replace it with P plus Q. Similarly here, replace P with P plus Q, and over here, with P plus Q, I'm not going to write the X because we have that at -1 over here. Okay, and you know what? Maybe for emphasis, let me put an extra multiply over here. Okay, so we plug in -1 into P plus Q, we get a number. We multiply that answer by this cube. Okay, so the rest is expanding this out, right? So what do we know about derivatives? If you want P plus Q prime, it's the same thing as P prime plus Q prime. Okay, so why don't we put the primes up here? There you go. And we can now erase that. Okay, so 3P prime plus Q prime. And you know what? We should not have that X and that X either. Okay, there you go. So same thing with the second derivative. Okay, we can compute P plus Q double prime as P double prime plus Q double prime. And we don't need that X anymore. Okay, what is the meaning of P plus Q at -1? You plug in -1 into P and into Q, and you add the answers to get the sum of 2 functions. Okay, and it looks like the rest of it is the distributive property. Okay, so copy one more time. And we get 3t prime plus 3q prime. Okay, and then over here, this 4x will distribute. So 4x times t double prime plus 4x times t double prime. Okay, what about over here? We can distribute that product. So we have p at -1 times that cubic plus q of -1 times that cubic. I have an extra plus over there. Okay, and of course we can see that if you put the terms with p's together, you get t of x. And if you put the terms with q's together, then you get t of q of x. All right, so we will leave the homogeneity part to you. Okay, our next item on our list is, of course, the main problem, which is to construct the matrix for this transformation. So we are going from P4 to P3, from a 5-dimensional to a 4-dimensional space. So our matrix, this matrix P, will be 4 by 5. 4 rows by, where's my right, by 5 columns. Okay, so remember that we switch the dimensions from 5 to 4, so it's going to be 4 by 5. Okay, so I hope you remember the recipe. We are going to plug in these 5 basis vectors, one at a time, into this formula. Okay, so let me make 5 copies. 1, 2, 3, 4, 5. Okay, so we will plug in 1 for p of x, the constant polynomial 1, x by itself, x squared by itself, x cubed by itself, and x to the 4th by itself. Okay, so you know what? I'm going to do what I usually do in my classrooms, and that is start with x to the 4th and work our way down. Okay, so what is the derivative of x to the 4th? 4x cubed. And then we have to find the second derivative. So it's the derivative of 4x cubed. That would be 12x squared. So we multiply by 12x squared. Plug in -1 into x to the 4th. We will just get 1. So we can erase that whole thing. And we have this. Okay, so the rest is arithmetic. How many x cubes will we get? 12, and this is 48, so that's 60 plus 2, 62x cubed. Okay, and then we don't have an x squared, so it will just be minus 5x. Okay, there you go. Do not trust a mathematician with arithmetic. Let's check. Oh wow, I got it right. Wonders never cease. So, next, x cubed. Derivative is 3x squared. 3x squared. Second derivative is 6x. So 4x times 6x. P of -1. -1 cubed is -1, so we will put a minus sign. How about that? Minus that thing. Okay, so we have a single -2x cubed, 9x squared, 24, 33x squared, plus 5x minus 7. Did I get that right? I think that's what I said. Okay, next, x squared. Derivative is 2x, and then the second derivative is 2. So 4x times 2. Plug in -1, you will get +1. So we can just solve that. And that's what we get. 2x cubed, no x squared, 6x, 8x, 14 minus 5, 9x plus 7. 2x cubed plus 9x plus 7. That's what I said. Okay, down to x. Derivative is 1, so we can erase the whole thing. Second derivative, 0. So this whole term goes away. P at -1 is just -1, so it becomes minus this thing. Okay, so we get minus 2x cubed plus 5x, 3 minus 7 minus 4. And we get, yep, that's what I said. Okay, now, save the best for last. Deep breath. The polynomial is the constant monomial 1. The answer is always 1. Okay? When you take the derivative, it's constant, so that's 0. If the first derivative is 0, the second derivative is also 0. Okay, what happens if you plug in -1 into the constant 1? The answer is always 1. So that whole thing is just 1. We can erase it. That is T of 1. Okay? So now we are ready to construct the matrix, because all we have to do is encode each of these answers into a 4x1 column matrix. But the order should be in 1x, x squared, x cubed. Okay? So let's insert a 4x5 matrix in here. 4x5. Okay, there we go. Scoot up so we can see better. Okay, here we go. So 1 goes into the first column. 1x, x squared, x cubed. So 7 minus 5. There is no x squared. 2x cubed. Okay, next. -4. Positive 5. There is again no x squared. Minus 2x. Okay. For x squared, we have 7 and 9x. No x squared and 2x cubed. X squared is getting cheaper. Okay, x cubed. Oh, finally, there's an x squared. It recovered. -7, 5, and then 33, and then -2. Okay, last column. 7, -5, back to 0. Poor x squared, and then 62 for the x. Okay, so that is our matrix for T, and it's 4x5, so obviously we're going to have at least one free variable. Okay, maybe we'll get 2 free variables. Who knows? All right, ready? Compute matrices aria. Ooh, so we only have one free variable. Okay. Leading ones are found in column 1, column 2, column 3, column 4. Free variable, 4th column. Okay. All right. So there's your aria. Let's put that on our next line. We can erase that now. find the basis for the kernel and for the range. Okay, so again, it's in 2 steps. So for the null space, we have one vector. Okay, and it's from R5. So let me borrow that. And our free variable is in column 5. It's been a while since we did a sight reading. That's 1. And then this will go into column 1 as positive 348/7. This will go in column 2 as positive 70. Column 3 as negative 75/7. Ooh, 0. Huh. So that's just 0 in the 4th entry. Okay. And yeah, I usually say I want integers. So therefore, so that's our null space basis. Okay. So therefore, a null space basis without fractions would be 348. 70 times 7 is 490. And then negative 75. And then 7. Okay. But remember, we're not finished yet. Okay. So now we need a basis for the kernel of T. And that would be, we have to decode these coordinates. And that would be with respect to the basis B for the domain. B is this. Okay. So decode the single vector with respect to the basis B for the domain. Okay. So the basis for the kernel would be these numbers, but written as a polynomial. So 348 plus 490x minus 75x squared. Yes, x squared. No x cubed. So we are left with 7x to the 4th. Okay, so we can erase this and this. There you go. Okay, so that is now a single polynomial from P4. Okay, so if we did this correctly, this will transform to the 0 polynomial in P3. You want to do that? Let's do that. Okay, we have the definition over here. Keep your fingers crossed. See if it works. Okay, check. Check, please. Okay, we need the first and the second derivative. Okay, so fortunately we have Maple to help us. Okay, so compute calculus, implicit differentiation, x. Okay, everybody knows the power. Okay, but again, it gives the answer in the usual order, highest to lowest degrees. Second derivative, so I can do compute calculus, again, second derivative. Okay, now plug in -1. I have a trick for that. I put square brackets, subscript, x equals -1. That means value. Have I used that before? I don't remember. We get -210. Okay, so let's put everything together. We want 3 times the first derivative, which was over here, plus 4x times second derivative. Second derivative is over here. And then p at -1 is this, so minus 210 times this. Okay, I'm almost scared to do this. Okay, is it going to turn out right? Let's try the cube first. 3 times 28 plus 4 times 84 minus 210 times 2 minus 420. 0. Okay, so let's click on the whole. And we get, oops, simplify, compute, simplify, 0. Okay, I don't know why it does that. Just give me the final answer. Come on. Okay, so that is in the kernel. It transforms into the 0 polynomial. Okay, now how about the range? Okay, so our leading variables are in columns 1 through 4. Okay, so the minimizing theorem says go back to the original matrix and take out, use columns 1 to 4 as your basis for the column space. Okay, but these are vectors from R4. We have to decode them now using the basis B prime. Okay, so that will be 7 minus 5x plus 2x cubed. Okay, but where did we see that? Oh, it's up there because this came from this. Okay, so basically what this tells us is that the first 4 outputs for t of 1, t of x, x squared, and x cubed, those are our basis vectors for the range of transformation. So I'm just going to copy these 4 vectors. So the last one is a linear combination of the first 4. Okay, so for the range, let me copy these. Okay, so I will just put basis for the range. And that will be, copy this, and then this, and then this, and finally this. Okay, so what's the rank? 1, 2, 3, 4 vectors. Okay, so it's rank 4. We already said that it can't possibly be 1-to-1 because your kernel is not just the 0 vector. Okay, so you don't pass the kernel test for injectivity. But is it on 2? Okay, what's the dimension of the codomain? P3 is 4-dimensional. Ooh, our rank is 4, so therefore it is on 2. Okay, so the rank of P is 4, which is the dimension of the codomain, which was P4. Let's just complete this. I'm sorry, P3, which is 4 dimensional. Okay, and so P is surjective, but not injective, since the kernel of P is not the 0 vector. Okay, it just fits. Alright, so back in chapter 3, we saw a dimension theorem for linear transformations. Okay, so we have that the rank of T plus the nullity of T is the dimension of the domain, or the number of columns in your matrix. Okay, so similarly for a linear transformation on abstract vector spaces, we have a dimension theorem in the case where the domain V is finite dimensional, if the dimension is n. Okay, so as before, we have the rank is the dimension of the range, the nullity is the dimension of the kernel. Both of these are integers. Okay, they could be 0, but they are integers. All right, so these two quantities are related by the rank plus the nullity is n, or the dimension of the domain. Okay? We used, of course, the matrix spaces to prove the dimension theorem, but there's a beautiful proof in this section for this theorem that doesn't use matrices at all. Okay? It basically grows a basis for the kernel, and then grows a basis for the range, but the number of vectors is exactly the dimension of the domain. Okay, so I hope that you take the time to read the proof of that. Now, we also already mentioned that when we went from P4 to P3, that it's impossible to be one-to-one. Okay, and of course that's because of our knowledge of our dimension theorem back in chapter 3, which we used by instinct for chapter 5. But now that we have the dimension theorem for abstract transformations, we have the same conclusions. Okay, so if your transformation is going from a smaller dimension to a bigger dimension, the transformation cannot be surjective. It can't be onto. But if it's going from a bigger dimension to a smaller dimension, then it cannot be one-to-one. Okay, so why does that follow from the dimension theorem? Okay, so if you're going from a bigger to a smaller, then the n is the dimension of your domain, and the rank is at most the dimension of the codomain, which is smaller than n. Okay, so therefore your nullity has to be positive. Okay, now what if you're going from smaller to bigger? Okay, then the maximum rank will be the dimension of the domain. Okay, but that's n. Okay, so therefore the rank cannot be n, okay, because the rank is smaller, strictly smaller than n. All right, so if you're going from smaller to bigger, then you cannot possibly be on 2. All right, so now we get to compose 2 transformations, but as before, we have to worry about whether they're compatible or not. Okay, how do we know they're compatible? If the codomain of the first transformation is the same as the domain of the second transformation. Okay, then if so, we can compose T2 compose T1 in that order, and it will go from the domain of T1 all the way to the codomain of T2, bypassing U. Okay, and it's essentially the same recipe. Start with a vector v in the domain capital V of T1. T1 of V is some vector u from capital U, the codomain. And then you can plug in u into T2. Okay, so you'll get some vector w from capital W. So the composition T2 compose T1 of V is T2 evaluated at T1 of V, which is of course T2 of U, which will be our W. Okay, so here is the diagram, and yes, that's exactly the same diagram that we saw in chapter 3. The only difference is that we had Rn, Rk, and Rm, but the rest of the symbols are exactly the same. Back in chapter 3, we said that you can compute the matrix of composition as a matrix product. Okay, so the only thing we have to worry about here in chapter 5 is how we created the 2 matrices. Okay, so this is where compatibility is very important, right? So we use the basis B for the domain V, a basis B prime for the codomain U, which we also use for the U in the domain for T2. Use the same basis, otherwise it's not compatible. Okay, and then we need a basis B double prime for W. Okay, so the matrix for the composition with respect to B and B double prime would be the product of the two matrices, right? If all three spaces are exactly the same, in other words, they're operators on the same space B, then it looks more natural. The matrix of the composition is just the product of the two matrices with respect to the same basis. Now, something even more special happens if T1 and T2 are actually the same transformation and they are, or it rather, is an operator. Okay? Then T composed T will be P squared, and the matrix of T squared is just the square of the matrix of T. Okay? So if you can take one self-composition, you can take another, you can take another, and so on. So you can take a total of R of them, and it's basically just the Rth power of the matrix. Okay, so of course we cannot finish the video without going back to our main goal, which is to learn techniques to help us solve differential equations, certain kinds of differential equations. So in our last videos, we were investigating this function space, which is preserved by the derivative. So the derivative of each of these functions is a linear combination of some of these functions, right? We already found the matrix of the derivative with respect to this basis, okay? So the derivative of the first function is negative 3x squared e to the minus 3x plus 2x e to the minus 3x, and there is no e to the minus 3x term, okay? Similarly for the derivative of x e to the minus 3x and the derivative of just e to the minus 3x, okay? So that's for the first derivative. Well, we can take a second derivative, okay? So the theorem just said, if you want the matrix for the second derivative, all you have to do is square this matrix, okay? So we can take that over here, and we can just square it, and we get, ooh, this is our matrix. So let's move that up. Okay, so that is the matrix for the second derivative, right? So we're making these building blocks because we're going to be looking at differential equations where you have something like 7 times the second derivative minus 4 times the first derivative plus the function itself has to be this linear combination, okay? So all of this is going to come together in 5.4. All right, so how do we use this? Okay, well, let us create a linear combination of these functions. Okay, so suppose you have the function, how about 6x squared e to the minus 3x minus 5x e to the minus 3x, and then how about plus 7 e to the minus 3. Okay, so find the second derivative of this function. B squared dx squared of that function. Okay, so of course, you can do this by hand. It will take you all of 2 minutes probably. How will we use this matrix? So remember the 3 steps. Encode, multiply, and decode. Okay, so yeah, you know what? Let me not be lazy. Okay, step 1, encode. Okay, so we want to create a column matrix which represents this function. Okay, so that will be 6x squared and then minus 5x plus 7. Okay, so remember in this convention we are going from highest power to lowest power. Okay, next step, multiply. So take our matrix, multiply by this, and we get, there you go. Oh, by the way, I forgot to mention last time. Notice that the matrix for the derivative is lower triangular. So is the square. Okay, I just noticed. So I thought, let me mention it here. Triangular matrices are obviously closed under addition. Not so obvious that they're also closed under multiplication. But they are. Okay, so we have that as the product. So as our final step, decode. Okay, so these are the coefficients for the three functions. And so we can now answer our question. So the correct coefficients are 54, negative 117, and plus 105. Okay, that's the second derivative, right? And of course, we have maple, so let's check. Oh, wise one. Compute, calculus, differentiation. Oh, that's only the first derivative. Compute, calculus, differentiation, another one. 105, yes, minus 117, yes, plus 54, yes. Okay, so of course that is the correct second derivative. Okay, now earlier we were talking about kernel and range. Okay, so let's take a look at this derivative operator. Here's the matrix. Let's find the REF. Oh, wait a minute. It's almost in REF. I can make a leading one there. Kill the 2. That 3 will survive my another. Do you see what I see? The REF should just be the identity. Compute matrices. REF. Oh yes, yes, it's just identity. Okay, so what can we conclude then? There are 3 leading variables. So the rank is 3. The dimension of the domain and the codomain are both 3. So it is on 2. D is on 2. There is no free variable. So D is also 1-to-1. The kernel is just the 0 vector. Okay, so D is both injective and surjective. Does that ring a bell to you? If we're going from R3 to R3 and the REF is identity, what matrix can you make? It's just the inverse. Okay, so in the next video, of course, we are going to look for the inverse of the derivative matrix. And of course, it has very important use. Okay, so on that, I will leave you once again in suspense. So thank you so much for watching this video. And until our next video, enjoy the rest of your day. Bye.